Okay, so we're going to go over the sum and difference, mostly the sum of two algebraic vectors. We have two algebraic vectors, vector A, which is also known as OA, which is at the component or point on our graph of 1 and 3. Vector OB, which is vector B, also has a component of 4 and negative 2. What it's telling us is it wants you to add up A plus B, and since A plus B is going to be equal to OC, okay, our new OC, we want to put OC in component form and in standard form, and we're going to figure out how to find the absolute value. So, and absolute value of OC, okay? And we'll talk about how that relates to each other, all of these. So let's put this in page width, scroll downwards. So what we're going to do is put a graph up here. Scale of 1, yeah, that should be enough. Okay. So first off, we had O we know starts here. OA was at 1 and 3. So we're looking at 1 x value, 3 y value. This is our OA, or as they said it, vector A. Okay. OB is at 4, negative 2. So this is our OB, or vector B. Okay. So vector B, this is point B, point A. They wanted us to add vector A plus B to create vector OC. Okay. So what that means is essentially we're going to move this other one over. Move this guy down. Okay. And it's going to make our new vector OC, this one. I don't think I've graphed it perfectly, but here's our OC, this point here. It should be up 1, 2. It should be up a little more, I believe. Yeah. Oh, that's better. There we go. There we go. So there's our OC. So this becomes coordinate C, and that's going to be our vector OC. Okay. Now, they want us to combine these two, and they put it in component form. So I'm going to show you. Obviously, we can look at the graph, and we can pretty much figure out what this component form is going to be, but we're going to prove this, adding up our vectors. Okay. So when we add our vectors, or we're looking for OC in this case, and they've given us a formula, and they usually call it AB. In our OC, what we're going to do is we're going to take x2 minus x1 and y2 minus y1. Okay, to find out our component vectors here. Oh, wait. No, we're not subtracting, right? So we take our values. OA was at 1 and 3, and or vector A, and vector B was at 4 and negative 2. Okay. Now, by looking at this, what is our point here? Anyone can tell? 5 and 1. That's right. So we're going to be adding these together. So we take 1 plus 4, and we take our 3 plus negative 2. This is going to give us our component value of OC. So when we do that, we're going to get 5 and obviously 1. The exact same as if we looked on the graph. Another way we could have represented this, though, is I could have represented vector A in standard form. What would vector A look like in standard form? Anyone know? Just vector A itself. Sorry, say it again. I plus 3j, yeah. I plus 3j. And vector B in our standard form would have been what? Minus 2j. That's right. How do we do a calculus? Okay, just grab a seat. So we're in our component form here. We could have also added our two component forms together where we had vector A plus vector B. Well, if vector A is equal to I plus 3j, and vector b is equal to 4i minus 2j. Remember, we went over these vector rules the other day. We said this was going to be vector OC. Vector OC will be equal to I plus 4i, which is 5i, and 3 minus 2j, which is just j, which relates to our component form of 5 and 1, the exact same values we had before. So we put those all together there. Now, let's say we're trying to find out the absolute value of OC. Let's zoom in again. Well, what we have here is a triangle. Okay. And because we have a triangle here, we need to find the magnitude of these lines, okay, in order to figure out the magnitude of our new resultant vector OC. So to find the magnitude of these lines, we use Pythagorean Theorem to solve every single one of them, okay? So let's scroll down a little. And what I'm going to be doing here, if you guys notice, is I'm going to be going down 2 over 4. So this has a value of 2, this has a value of 4, this would be our hypotenuse. And that would give us our value of vector B. And then to find the value of technically vector A, the magnitude of it, it's over 1 up 3. Well, that's a value of 1 and 3. We use Pythagorean's theorem to solve that one too. Okay? Once we have that, we'll have the values of these two. And we can then try to use it to solve for our last value here of our components. Okay? Now what we're going to do, quickly show how that's done. What were our values again? 5 and 3. Say it again. Okay, so from where we were, we just put this into standard basis form, our OC vector. It then asked us for the absolute value. We scrolled up here. We wanted the absolute value of OC. Now, to find the absolute value of OC, okay, because we know the component, or the number of it, it's actually quite easy to solve. Now, looking at it, we talked about how what we want to do is essentially use Pythagorean's theorem, and this goes out 5 and up 1, which means this is a side length of 1 and this is a side length of 5. And we could use this idea to find the distances of all of the sides of this triangle, since we don't have the magnitude of any of them. But instead of actually counting it out and stuff like that, because everything is originating from the origin, it's actually very, very easy to figure out what these side lengths are. Instead of counting on a graph, we know this is 1 and this is 5. Well, that's exactly what their x and y values are. The y value is 1, therefore this length of that side of the triangle is 1. This x value is 5, therefore that side of the triangle is 5. So we could create a right angle triangle with just our components right here. We can find them quite quickly doing that. And we're going to show you the 2 ways we could have done that. Oops. So, other way. There we go. Okay, so we have that component there, OC, and I'm going to show you using OB and OA how we would have got the same answer by finding the component in OC. So we're going to try to do this 2 different ways so that it makes sense for everything. So, because we're finding the differences or the side lengths, technically to find the side lengths between OB and OA, or in our case our OC, we could add them together. And that's going to give us our OC side length. So our OC side length, let's figure this out using Pythagorean's theorem. We know that our OC, which is the hypotenuse, is technically, if we want the absolute value of it, squared. Because Pythagorean's theorem is c squared is equal to a squared plus b squared. Okay. Our a value could be the x or the y, so we'll put it in as 5 in this case, plus 1 in this case. Now, instead of having it as OC squared, I'm going to bring the squared over and make it square root. So the absolute value of OC, which is exactly what we're looking for, is equal to the root of 5 squared, which is 25, plus 1. So OC, or the magnitude of OC, the absolute value, is root 26. We're going to leave it as a root because when we put it in a decimal, it's far less exact when going through it. Okay. Now, let's say we have position vectors that are a little different. Let's say we are looking for the position between two vectors. We're looking for the magnitude of a line between two vectors. Okay? So I'm going to jump to another page here. And what we're going to do, bring that up again. Okay, let's say we have two position vectors. One of them, we'll call this our OA and our OB. Okay, so this is our B. Again, O because we're at the origin. This is our A. Well, this coordinate here is 4 and 4. And this coordinate here is -6 and 7. Okay. Now, we have a formula when we're trying to find AB. Okay? Let's say we're trying to find vector AB in this case. Well, vector AB has nothing to do with adding or subtracting in this case. Vector AB is essentially the tip of A to the tip of B. So vector AB is this vector in between the two of them there. Now there's a couple ways we can go about solving this, but what's key here is this vector, when we added them before, remember we were going from the origin. So we know that our 2 points, or our component points, can be subbed right in to find the absolute value of this. So let's say in this question they've asked us to first of all find out AB, what is vector AB in this case, if it were to be turned into a vector from the origin. So what we're going to do in this one is we're going to move this position. This vector AB is not at the origin. We would like to know what it would look like if it was going out from the origin. And we're also going to try to find out the magnitude of this vector. Okay, so the other part of this question is what is the magnitude of vector AB? So we have this vector here. Now on a graph, because of my computer, I can easily grab it, drag it over, and estimate where it is. But we want to actually know what would the components be, or what would the actual points on a graph be for this vector. And in order to do that, what we do is this is where our formula is. Let's say we have A, which is x1 and y1. And we have point B, which is x2 and y2. If this is the case, then vector AB, because it's not from our origin, is essentially x2 minus x1 and y2 minus y1. So we actually have to figure out what our points were. Well, in this case, our point A was 4 and 4. And our point B was -6 and 7. So we plug those in to find out what AB is. Okay? AB in this case would be 4 subtract -6 and 4 subtract 7. So we end up with 10 and -3. 3, x2. Oh, did I do that backwards? Sorry. Yeah, I did that backwards when I plugged them in. I apologize. X2 is our -6. That makes more sense. -6 subtract 4. That makes much more sense. And y2 being 7, subtract 4. So we get 3 and -10. That's better. Okay. So what that's saying is if I were to move this vector AB back to the origin, so it has a point at the origin, and maybe at that point call it OP, or as our point, our vector would actually be at -10 and 3. Okay. So let's see if this actually works. Make this an infinite clip. Whoa. So when we move this vector to the origin, that's exactly what we'd be looking at. Had it been going out of the origin, its component part would be at 10, or negative 10, and 3. Okay, but another part of the question was to find the magnitude of this vector. Now there are two ways we could have done this. First of all, by finding its component parts here at negative 10 and 3, it becomes very easy to put this in the Pythagorean Theorem because we know that this is 3, the height of one side of the triangle, and the base of the triangle is 10. So we know 3 squared, 10 squared are going to be our numbers. But the other way we could do this, and they've done it in a formula for us, is the absolute value of that same vector, AB. Let's say we hadn't put it into its position vector at the origin. Would be written like this: the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay. This is also known as like a distance formula. When you guys are in grade line, finding the distance of a line, which is essentially the magnitude of this vector. It's quite straightforward. We're going to piece it together and show how it's quite closely related to the components of this vector. So our x2 and our x1 are the exact same that we had before. Our x2 being negative 6 minus 4, and then we're going to square it, plus 7 minus 4 squared. This will give us our negative 10 plus 3 in this case, all square rooted. So the root, all squared also, gives us 100 plus 9, which gives us the root of 109. Again, not an even whole number, so we're just going to leave it in our radical form. The distance of line AB is root 109 in this case. Yeah, that would be considered our magnitude. So we have a position vector. At the bottom here? The square and the square root. No, we have to, because these are our brackets here, we're squaring them. And what you want you to think of is because there's an addition in between, the addition needs to be done before we can square root. So think of it as they're both separate almost, and then we're adding them together. Okay, the square root is being done because what I want you guys to relate this to is this is actually very close to Pythagorean's theorem again. What they've done here, in this case, is they've drawn a triangle like this and found out the side lengths. Well, x2 minus x1, which is negative 10, is this side length right here. So we know that this is 10. Negative 10 because it's going in the backwards fashion, but it's fine. It's still an absolute value of 10. Well, this height here, in this case, is 3. Goes up 1, 2, 3. Okay? So all they've done is created another triangle and solved the hypotenuse using Pythagorean's theorem. So these were to find the side lengths of the triangle. And then in Pythagorean's theorem, we do the side length squared plus the side length squared, which is essentially this. Side length squared plus side length squared is equal to the hypotenuse squared. So we add them together, and then technically, because our hypotenuse, which is usually c squared, we usually bring the squared over from this side over last and square root it. That's what we're going with. We're just a play on Pythagorean's theorem. Okay?